Welcome along, ladies and gentlemen, to your weekly SETI seminar series. So we're very lucky to be joined by Michael Way, who's come across to us from the East Coast. He's visiting for the fall AGU meeting here in San Francisco. And Michael started his career in the Department of Physics at University of Missouri, and then went to Princeton for 3 years, and then moved across to the West Coast to NASA Ames, and then moved across to the Goddard Institute of Space Studies, where he is in the city of New York there. Today he's going to talk to us about recent work that he's been doing on the global GCM model over there, and adopting it to looking at habitable zones and the like for planets in our solar system, and also, of course, other solar systems. So please join me in welcoming Michael.
Thank you, Adrian, and thank you for the invitation. Really appreciate it. So yeah, this is a relatively new project that we began at the Goddard Institute for Space Studies about 2 years ago. We have some internal interest in modeling other worlds, and we have a pretty decent 3D GCM that we use for modeling Earth climate. And so we have made some efforts, and with some internal funding from Goddard Space Flight Center, to expand the capabilities, basically to expand the dynamic range of our model to be able to model some other worlds. So I'm going to talk about half of that work, which is pushing the model to warmer climates. Our goal, of course, is to get to worlds like Paleo-Venus and maybe even eventually modern-day Venus, which will be tougher for our model. And there's another effort to push it out to the cold side. And we have a Mars model that's running. It's missing some key components, but we expect in 6 months our model will be able to do a pretty good job for Mars. And we actually recently got some funding to even extend the capabilities all the way out to Titan's atmosphere. Very, very cold, obviously. There's chemistry, but we have some very good chemistry people in-house. We have to adjust our radiation, which we also have funding for. So I think we're in a good spot. So I'm going to talk about the warmer side of that, as I said. And this work is all made possible mostly by Anthony Del Genio, or Tony Del Genio, who is our resident cloud expert in a sense, but Tony's been working with our GCM for the last 30 years. And the other three people here are our main developers, Max Kelly, Igor Alienov, and Thomas Clooney. Tom is at Goddard Space Flight Center. He's also a physicist, and well, so is Max, so are Max and Igor. So they're really the team that made this work possible. And you see it's a bit preliminary. I don't have everything done. We're just at an incredibly fast development cycle. You know, we find problems with a model that it was never designed to solve, and we fix those problems and move on to the next. We find another problem, we fix that problem. So I'm really showing you runs that I finished on our supercomputer 3 days ago. I mean, at the very end. I mean, really, I'm at the limit of what we could do. So I'm going to try to show you three things. How we're going to probe the inner edge with our model. For some reason, the fonts have disappeared. That's what happens when you go from PowerPoint to PDF, I guess. Our objective is also to compare our results with other 3D GCMs. I'm going to show you a little bit of that ability, and also show you which aspects of our GCM is robust and which seem to be much more model dependent, which is a big concern with people using 3D GCMs. So let me try to first motivate why we want to do 3D models. Let me start with the negatives, because of course my list of positive is much bigger. 1D people are not fond of 3D GCMs because they think they're too complex. There's a lot of physics to encode, and they're right. It is very complex. It's inefficient. Of course, a 1D model, you can do all kinds of parameterization studies in a fraction of the time you can do a 3D GCM. Whereas our model, and I'm running the low resolution version of our model runs at several resolution versions, and the resolution is a big part of determining how fast the model will run. It runs about 4 minutes per Earth month on about 20 cores on our supercomputers at Goddard. And it would run the same here at NASA if we ran it here. And hubris, well, just because you have 3D model doesn't mean you know the answer. That would be another complaint about 3D models, I think. But I think the pros, and again, compared to 1D models, is we can look at rotation effects, which I'm going to spend quite a bit of time today talking about. Horizontal heat transports, which 1D models cannot do. Cloud feedbacks, they can do some of that, but I would say so far their record is not spectacular. And a whole list of other things, dynamical estimates of water loss limit. You don't have to ignore things that are uncertain in the 1D. We can put them in our 3D models, so it's feasible. Potential to think about seasonal effects or regional habitability. In a 1D model, you can't look at regionality, of course. And that is very important. We see that in other simulations. Our model has done paleoclimate runs, actually, where we see in, say, the Neoproterozoic, where other models have shown that the Earth ices over completely. Our group has shown that that's not the case and that there's a band of habitability right at the equator, and the planet never does actually ice over. So that's something that your 3D GCM can do as well. Time-evolving synthetic spectra, so we can mimic how we can detect rotation and other aspects of the model from space, because that's our ultimate goal, of course. And I would say our biggest advantage, at least in the 3D realm for our group, is that all the development that we are doing with this model for other worlds is all done by the same people who are already funded to develop this model for Earth climate. So if I have a problem in the planetary boundary layer, or I have a problem in the radiation, or if I have a problem with the chemistry, I can walk down the hall or I can walk up 2 floors and talk to the person that did the coding, and I can get a solution within a couple days. And there's not many groups that can do that, that are doing this kind of work right now. Often people are taking the NCAR-CAM model, or they're taking somebody else's model and they're modifying it, and they're totally dependent upon that group's willingness to communicate with them about it, and they're not funded to communicate with you. They just have to do it out of the kindness of their hearts. And we know that there is a limited reservoir of that in these funding times. So I think that's one of the things we're going to bring. And the LMD group in France acts the same way. They're a very similar group to us, and we think that we're going to be able to do a lot of really interesting comparisons with them over the years. Okay, so one question I think we have is, how do we quantify the model uncertainty? That's one of the big questions about these 3D GCMs. And the 2 ways that we try to do it are the free parameters. Of course, there are many free parameters. But in this case, in this talk today, I'm going to talk mostly about the atmospheric constituents and the cloud parameterization schemes that exist. Clouds, people are finding, are very, very important for Earth climate. And of course, they're very, very important for modeling other worlds. If any of you know about faint young sun paradox, clouds are heavily invoked to solve those issues. When the sun was 20% less luminous than it was today, did Earth have habitable conditions? How did it have habitable conditions? If you look at Mars during the faint young sun period, Mars is a very cold place. How do you make it warm enough to have liquid water that we think existed there 3 billion years ago? That's very tough, and clouds are often invoked to solve those problems. And multimodal studies. So compare with other 3D GCM models and see what kind of answers they get, and see if we're ending up with similar answers, even though we parameterize things very differently. So, we're not using any components from the NCAR-CAM model or the LMD model. Everything is done completely separate from them. So then when we do comparisons, they really are independent in a sense. And I think that that's super important for us to qualify our uncertainty. And that is also done in the climate community. That's how they do things with climate response to CO2 and the IPCC reports that are published. That's all about multiple intercomparison in essence. Okay, here's another motivator. This is a picture from Yang et al. 2014 this year that shows some 3D model results that they have versus 1D model results. And you can see from this plot, if you look at here, they have 3D inner edge for slowly rotating and tidally locked planets. And that's from the CAM3 model. These people use the CAM3 model. And 3D inner edge for rapidly rotating planets. You can see they give quite different results from what a 1D model gives you for inner versus outer edge of the habitable zone. So again, there's a very strong reason to better understand what these 1D models are telling us versus the 3D models. And this is a plot from Koparapu. I think he's coming to give a talk in January, I think, Ravi. And here you can see just some results from cloud-free models where they have a habitable zone here, and they show how you get runaway greenhouse depending on what the effective flux is. You can see early Mars sitting out here just outside the habitable zone, as I talked a little bit ago. These are all things we want to explore. We want to be able to explore these parameter spaces with our model. And as I said, we've made some small progress in that. So let me just tell you a little bit about our model setup, what kind of world we're talking about. Really, our initial idea was to mimic the world that Yang et al. Set up in their early 2014 paper, so we can make comparisons to them, because they had some very interesting results that intrigued us, and we wanted to see, will our model get very similar results to what this team has? So you can see, first of all, again, I use the low resolution version of our model, so it's a 4x5 lat long grid and 20 levels in the atmosphere. We don't have any eccentricity in this world, no obliquity in this world. That causes all kinds of interesting effects, which maybe I'll have time to talk about. We set all the land albedos to 0.2 as they do. At the model start, they can evolve, of course. No vegetation. We turn off all of our vegetation calculations in the model. I set the ocean depth to 100 meters, and I set the fluxes to 0. That means that a given cell is 100 meters deep, and they do not communicate with each other, the ocean cells. In terms of, they only communicate with the atmosphere. Okay, I know you guys are saying, "What, are you crazy?" But this is what they did for their model setup, and there's some advantages to doing it. First of all, it's very fast, and if you want to explore certain parameters in your model, you have to do some things a little simpler. Now, I did some dynamic ocean runs, a fully coupled dynamic ocean, full depth, 5,000 meter depth ocean. But to reach a temperature equilibrium in that ocean takes a few thousand years of simulation, and that's months of computational time. And my AGU poster is tomorrow, and I didn't have time to do all those runs. Yes, Kriyan?
Does that mean there's 100 meter depth ocean cell right at the surface? And that's
Anywhere that you see ocean on a map of the world, it's 100 meters depth. That's what it means. In one cell, yeah. In every cell.
4x5.
Yeah, in the 4x5 cell. Exactly. I know, it sounds a little strange. When I first did that, I thought it was also a little strange too, but I was assured that this is not uncommon. Often what actually Earth people do is they do a dynamic ocean run, and they set up a Q-flux ocean, but using the dynamic ocean, they know what the transport fluxes are between grid cells, and so they can change the Q-flux model to actually mimic that. Since I hadn't done the dynamic runs for all of the different solar installations I'm going to show you, I couldn't do that for this run either. But again, this is what the Yang et al. Group did, and I wanted to see how our model responded to their parameterization setup. Of course, we have an Earth continental layout, and I have a range of rotation periods. That was one of our big development pushes earlier this spring, was to allow our model to be slowed down. So I'm going to show you Earth rotation, or rotation rates that are 1 Earth day, 16 Earth days, 64, 128, 256, and I even have done some tidally locked runs. Now by day, I mean sidereal day. Those are a little different from solar days. That doesn't have a huge effect until you get out to like 256 and such. A solar day at 256 solar days, sidereal days, is about 800 days long, so quite long days. And this is the part where we changed a few things for reasons that would take a while to go into, but partly because of the way we've been developing the model. So in the first scheme I'm going to talk about, which I'm going to refer to as case A, and for those of you that have the handout, you can see case A and B mentioned in the handout. The handout is just my poster presentation at AGU, but it has more or less most of the information here. So we keep nitrogen. It's a non-reactive gas. Radiation doesn't really see it, of course, so it's not a big deal whether it's there or not. CO2 is set to 1850 levels for Earth, 285 parts per million. CH4 is set to 0.7, again, 1850 levels. And I use a cloud parameterization scheme, which I call parameterization scheme 1, and I'll talk about what these weird numbers I am talking about here, U naught A and U naught. You're seeing the internals of our coding scheme with arbitrary names for things. But I'm going to talk a little bit about what they are and what influence they have on the climate of this world. And the second, I raised the CO2 to 400. That's what Yang et al. Do, and they reached CH4 to 1. And then I also have changed the parameterization schemes a little bit too. There are no aerosols in this world, no anthropogenic gases, no O2, no N2O. There is some ozone. That's an unfortunate consequence of our radiation scheme. I could not take the ozone out right now. We're working on getting it out for reasons that would take a while to explain. That means that we have a stratosphere and we have a tropopause. If you take the ozone out of your model, that effect, the world looks very different in that regime. So, but I don't think it affects our results in a huge amount. I was able to do some runs without the ozone, and things were not markedly different. But I'll know more by spring of 2015. Okay, so let me just talk quickly, just a little bit, just to give you a feel for these cloud parameterization schemes that I've used. So again, I'm referring to case A and case B. So here, there was this parameterization I call U naught A, which again you can see in that handout. And as I go from case A to case B to case A, I'm decreasing the clouds, or from case A to case B, you can think that I'm increasing the clouds in these upper levels of the atmospheric model. And in U naught B, it's the opposite. From case A to case B, I decrease the low-level clouds. And I'll talk about what that means. That means that as you increase the clouds down at this level, at the 850 millibar level, you're going to increase the effect of shortwave radiation in your model and on the Earth versus the long-wave effects. And up here, it's the opposite. When you change the effect up here, you're going to increase the effect of long-wave radiation on your planet versus the shortwave effects. And there's one other parameterization that we change, which is something we call the WMUI multiplier. It means nothing, of course, to you. But it creates more water ice clouds in the model. It changes actually the number concentration of ice in the clouds, just to see what kind of effect that would have. And that has effects at towards the equator at high latitudes or high altitudes where you would get some water ice clouds. And of course, that effect grows as you go to higher latitudes in your world. So those are the things I've changed, at least in the cloud realm. There are, of course, other things you can change in the cloud realm, but these are the things that we thought would have the biggest influence on our model. And you'll see what the influence is in the long run. So these plots here are some of the results, and I'll come back to them a bit more after I explain a bit more of the cloud parameterizations. But the plot on the upper right is the result from Yang et al. In 2014. And that's what I really wanted to see if our model could mimic. Could our model come up with similar plots? So what you have here on the x-axis in all these plots is the stellar flux. And on the y-axis, you have the global mean temperature for this world. Now, I'm going to talk in more detail about this, but what I want to focus on just in the very beginning here and point out is the starting temperature for this world at Earth rotation rate. So you can see that's where the blue arrows are pointing to in these plots. In the Yang et al. World, again, this is a zero obliquity world with different Earth concentrations. Their world, funny enough, starts around 287 K. It's very similar to Earth's global surface temperature. Very interesting. I didn't notice that when I first read the paper, but I thought it was really fascinating how they could get a world that was not Earth but has the surface temperature of Earth. So they have done something to this model which they have not told us about. Okay, when you read the paper, they don't tell you how they got that temperature, but there's no way they ran the CAM model in this state and got this temperature without changing something. I'm going to tell you what we changed. Okay? If you look at our model, the first time I ran the model, before I did any changes in essence, I got this pink line, which I call 1 ode, or magenta line, which I call 1 ode. And our model, this again, I just took the Earth model and I changed the obliquity and the eccentricity, the land albedo, got rid of the land ice. Our model started out at 263 K. So it's quite a bit colder than that Yang world. What does that mean? Well, that means as I increase the solar insolation, which you see going here, this is solar insolation of 10% more, 20%, 30, and 40, I can get up to 40% more solar insolation before my radiation says, it's too hot, I don't like this, and I will not run anymore. Okay, in their world, they get nowhere close to that. So I basically reach a Paleo-Venus type solar insolation for this particular model. They get nowhere close to that. Their Paleo-Venus is this early Venus line. It's way over here. Their model gets too hot too soon. But that's because they started at a much warmer temperature. Now, again, how they got there, I don't know. But again, I'm going to tell you how we got there. So I made some tweaks to the model. Our model is always under continual development, and we're working on a branch of the model that doesn't get as much development as the main branch. The main branch is a 2 by 2.5 grid model, and actually we're going to a cube sphere model. It'll be a degree by degree. But again, because I wanted to do rapid development, I couldn't run that model because it takes 3 times as long to run a time step. So I wanted to, get something done. So I made some small changes, and then I got this next line here. I made some shortwave changes to the model, and I got 269K. Still quite cool. I couldn't quite get to Paleo-Venus, but I got close with that model before the radiation coughed up and said, no, thank you, it's too hot. I don't know the answers for you. And then down here, you can see where I tried to actually use the cloud tunings, which I've talked about, and some other things to get the temperature close to Earth. So more or less what Yang did. I couldn't quite get Earth's temperature, but I got 291K for my starting point. Again, that's this black point over here. I'll show you on this side, this point. So I'm going to talk mostly about this particular parameterization scheme where I use the increased CO2 and CH4 on the bottom. And I'm going to talk about this one, not that pink line, but all the other lines in this plot, where the model starts at 269K, okay? So I've told you a little bit of what goes under the covers in terms of where my model starts out. Okay, so again, let's just look at changes to our greenhouse gas concentrations from 285 to 400 and CH4 0.7 to 1, and these high cloud ice forcings. I'm going to talk about those two things a little bit. Okay. What does changes to those high ice cloud forcings do? Okay, so first I'm going to show you what we call shortwave cloud radiative forcing. That's what the CRF is. I'm sorry for the acronym. I couldn't fit it on my slide. Shortwave cloud radiative forcing, that term that you're going to see in these plots is just the absorbed shortwave by those clouds minus the clear sky absorbed shortwave if there were no clouds. That number tends to be negative, which means that these clouds cool the Earth. And the long wave cloud radiative forcing, and that's what would be the clear sky outgoing long wave from the surface of the Earth minus the actual outgoing. So how much of the clouds are trapping of the long wave radiation. Now, those high ice clouds, if I increase this thing called the WMUI multiplier, which I mentioned before, I increase the optical depth of the clouds in essence, and again, I trap more long wave radiation. That tends to increase the temperature of my world. So here what I'm showing you is where I've done the latter. I keep the CO2 concentrations fixed at 400. I change that ice cloud concentration to a higher value, and you can see in the long wave, indeed, I go from a long wave forcing, and this on the x-axis is how many years the model run, because I want to make sure the model's in equilibrium. This better be a flat line, otherwise I haven't reached equilibrium yet. Again, if I ran a dynamic ocean, I'd have to run this thing an order of magnitude longer to get even close to the right result. Really, magnitude and a half would be better. And here you can see some of the differences. So it gave 15 watts for the cloud radiative forcing before I changed the parameterization, and now it gives 17. So I got 3 extra watts by just changing the cloud, the amount of ice in these very high clouds. In the short wave, you see the opposite effect. So here for the original value, it got minus 37 and it increased to minus 40. So that also has an effect on these clouds. And then you can look at the net. That's the long wave plus the short wave. The short wave is a negative number. And you can see that when I went from the original value in green to the original value in purple, it changed a small amount. So my net cloud radiative forcing was minus 22, and it went to minus 23. So a small amount of change in that net radiative forcing. But that also changes some other things. It changes the albedo of the planet a little bit. And I put the numbers up here. It moved from 27.2 or 0.27 for those of you that use albedo units to a little below 27%. So the albedo of the planet has changed. The global albedo of the planet has changed a little bit by changing those cloud condensation, the amount of ice in those clouds. And you can see what we call the greenhouse effect has also changed a little bit. So I went from 34 in the forcing from greenhouse to 37. So you can see that effect shows up in my surface temperature plot, which you get over here. So I get about 3K from that. Now, one thing you're going to see immediately is that that green line is not flat. So this model is not quite in equilibrium. Okay, I don't have the data to show you, but this line does level off shortly thereafter. So it's not too far off from what the reality is. So just by changing one of the parameterizations in these high ice clouds, I can get 3K difference in warming of this world. Okay, so that's probably one of the kind of things that the Yang group did. I don't know what they did, but I imagine that's one of the kind of things they did. Here's the other one. Let's look at just the greenhouse gas forcing. I think everybody knows about climate change and all that kind of stuff. So this is just keeping that cloud ice number the same between the two runs and just changing the greenhouse gas concentrations from, as I said, 285 to 400 and changing the CH4 from 0.1 from 0.7 to 1. And here you get a different kind of effect. Here, when we went to higher values in the long wave, I went from a long wave forcing that was from 16 to 17, so the long wave increased, which is what I expect when I increase the greenhouse, the forcings a little bit. The clouds see that too. The shortwave forcing has also changed, but by a very small amount. It's not affecting the clouds so much. But you can see a bigger change in the greenhouse forcings between these two, where I went from 35 to 37. And then here's that temperature plot again, just keeping everything fixed, but just changing the greenhouse gas concentrations, and I get 3K for this world, okay? So now you've seen how I moved from that lower point in the beginning at 269, how I got part of my way up to 290, okay? Again, I'm sure the Yang et al. Group did some similar things. Yes, Kriyan?
Change both of them so you got 3K.
Yes, I'm getting there, absolutely. Good. That's what this is. So Kriyan's on it. Here I've changed both at the same time. I'm not going to go into the details. I've already shown you this, and I could go into it, but it would take some time. But the idea is that adding those two effects, you get about 6K of warming. Just changing those two things, the greenhouse gas concentrations and these high ice clouds. And here they are up against each other. So you can see how those forcings work out and how these two sum up to give you 6K. All right. Let's go back to the tuning for a minute, the other tuning thing I mentioned. So here is with, as I said, the GHG and WMI give me about 6K of a 22K difference between these cases. The other 16K of that increase, the other 16 Kelvin in that temperature, that global temperature, are the results of other tunings we did to the high and the low-level cloud fractions, the cloud fractions. So we increase the amount of coverage at the high clouds and the low clouds. And for those of you that know something about faint young sun, will be very familiar with this kind of tuning that is done. So again, this is that same plot I showed you before, where I move from this point, 269, up to 290. Yeah, please.
Is the reason you did this tuning just to get a matchup with their code, or is there some more fundamental reason?
It's a good question. Sorry, I'm not making it clear. So what I'm saying is I want to try exactly to get at the same get near the same starting point they did. Even if I don't agree with their starting point, I should try to get to around the same starting point they did so that my world mimics their world a little better. And there are many ways to get to their starting point. But I wanted to try to make my model mimic theirs as much as possible. So one way to do that would be to increase the greenhouse gas concentrations to the levels they did, but I only get 3K by doing that. So I can't get to their starting point of 287K by just doing that, okay, from 269K. So I did that first. Secondly, I changed those high ice clouds a small amount to see what kind of effect. I get another 3K from that. And now I'm going to change some other aspects of the clouds to get my model to mimic theirs as much as possible. Sure.
Well, is this, you're trying to validate your model?
Yeah, I'm trying to validate my model against their model. I want to see when my model is set up very similar to theirs, as far as I know, how close are the results between the two. And you'll see in the end the results of that.
Do you know what all the different occasions and everything are?
I don't know that much about their tunings. I know the CAM model, the NCAR model, but I don't know all the tunings that they have used to get this temperature. That's what I've said from the start. I don't know what they have done in that model because they don't make it clear in the paper what they've done. I'm telling you what we have done, which we will publish in the coming year.
But you know their curves, and that you're going to get, the idea is if you set up initial starting points that match their thing, you get curves that match theirs.
I should get curves that match theirs. If I don't get curves that match theirs, I would be a little worried about either their model or my model, or both. That's the idea. That's the idea. Okay, so let me, again, I hate to bog you down with all this cloud stuff, but I promise you, you're going to see more talks about clouds when people talk about the inner or the outer edge of the habitable zone. There's no way to avoid dealing with clouds. So I'm immersing you in clouds for a reason. You're going to be forced to deal with them over the long term as well. So these are some other knobs we have. As I said, this U naught not A and U naught not B knobs. If I change the U naught not B knob, if I increase the value, it doesn't matter so much. That's a fact. But from case A to case B, I should get less low-level clouds. That's the idea here. And in case B, or in the other case, U naught not A, when I increase that number, I can get more high-level clouds. So I trap more long wavelength radiation. So, as I said, I need 16K. So which of these knobs do you think I'm going to turn? I'm going to turn the U naught not A knob to try to get more clouds to trap more long wave radiation. And I'm going to change a little bit of those low-level clouds that deal with the shortwave radiation. But that's not the big effect here. Okay, so I'm not going to go into so many details about that. But let's go back to what these results that we have show us. Okay, so here is a plot of surface temperature, albedo, ocean fraction. But let's just focus on the surface temperature now. The first thing I want you to notice is there a large gap in our runs. Regardless, this is our case A and our case B run. There's a large gap here between rotation periods of Earth rotation day and 16 times Earth day. That's the red line in these plots right here. Okay, the red line and the black line, red line and the black line here. And then the other part of the plot, you see what it is for a 64 days long on this planet, 128 and 256. And the Yang et al. Group see something similar. They don't see it quite as pronounced, but it's a similar effect. The first thing I would say is that you can see that regardless of the cloud parameterizations I've used, and to some extent the greenhouse forcings, the gap is still there. It's not a gigantic effect, it turns out, even though I've started at quite a different temperature. What does the model actually show up? Our model shows exactly what these people describe, that by slowing down the rotation of the planet, a lot of clouds build up on the side facing the star. Okay? What does that do? That increases your albedo, right? You get a lot more clouds, you got a lot more reflected sunlight, and it doesn't get as warm down on the Earth. Also, the other thing that happens, of course, as you slow the rotation down to the planet, the backside of the planet spends a lot more time looking to outer space, and it has time to cool down, right? So those are the two big effects you're seeing here in that gap. And we see that, again, in the 16 to 64 day regime. Why is that? Okay. Well, again, I think part of the temperature difference is because of this cloud buildup. But the other thing is that what we think, we don't know for sure, but our belief is that this has to do with the radiative relaxation time. So on Earth, we're spinning very fast. The radiative relaxation time is slower than the spin rate of the Earth. How do you know that? Well, when you go outside at night and it's 2 o'clock in the morning, it's not freezing cold, right? It's colder, but it's not really cold. That means that all of the heating of the atmosphere, all that radiation that you've trapped, has not escaped. It hasn't had time to escape to space. But when you're slowing down this rotation rate, you change the effect, right? So that the planet's heating down on it, and you've changed the radiative relaxation time as well, so that it has time to move heat from the front to the back of your planet because it's rotating so slowly, in addition to those cloud effects. Okay, this is a difference of those plots of our different cases. And again, you see this very large gap regardless of the parameterization scheme. So this was the one Earth day case for parameterization B versus an A. Here's 16 day versus B. And then again, as you go to higher these longer days, things kind of bunch up down here. So that tells you there's something fundamentally different going on in this world, and that the cloud parameterizations, in the end, I told you all about clouds, but it turns out they're not super important to the end result. That's what's amazing about it. So maybe that's why they didn't mention it so much in their paper, all the things that they did. I don't know. What else happens in the slowly rotating world?
But it was super important for your getting your starting temperature.
Exactly, exactly. It was super important for my starting temperature. Absolutely. But in the end result, when I slowed the world down, it didn't have a huge effect, it turned out. The other thing that changes, of course, when you slow down a world is that your Hadley cell changes, right? On Earth, our Hadley cells give us a lot of rain in the tropics, right? And they give us our deserts, right? Because they're quite small, that's because they're rotating rapidly, and the Coriolis effect gives us those smaller Hadley cells. But as we slow down the world, that Coriolis effect is diminished. Here I'm showing you the size of the Hadley cells for a normal Earth world. Quite narrow. This is latitude, in essence, and the length of that Hadley cell. And here's a 128-day rotation period. And you can see the Hadley cell has grown immensely. This Hadley cell is the size of the Hadley cell that would exist on Venus, in essence. Has one northern hemisphere cell and one southern hemisphere cell. So that's the other huge change that has happened when you slow down this world. The Hadley cells are changing in size. I was going to show a movie, but I'm using a PDF file. But you can see in the very slowly rotating world, the 128-day case, you can see as the sun is hitting different parts of the world for long periods of time and not, and how the world is cooling down in different regions of the world. That's another coding thing we did, which I didn't have time to show. I really wanted to show, my goal was really to show this plot, but with the hottest point on the planet, at the point where the sun, where the sun was hitting it the hardest in these worlds. And I just finally got our developers to get our diagnostic package to print out all the numbers for that for every time step, so that I could get it, I can average over an hour or 2 hours. Right now I have to average over a full day or a full month, but now, when I get back, I'll be able to actually get that data out and tell you what is the temperature and the hottest point on that planet, and does it look like this? Because I'm averaging across the whole planet here, right? That's a little bit of a fake number. That's a little game that's played, I think, in a sense, because I told you that the night side of this world is going to get very cold because it spends a lot of time looking at outer space, and the bright side is going to get very warm. I know for a fact that the bright side is not getting super warm because our radiation code would crash if it did, to be honest, and theirs does too. That's why you see this cutoff in all these plots up here, almost at around 320K. Their model peters out around then as well. Not because the whole planet's at 320K, it's because a certain part of the world has probably reached in a grid cell around 60 centigrade or 70 centigrade, and the radiation schemes aren't really valid for temperatures 70, 80 centigrade. They just can't handle that. They're not designed to handle that because these are Earth models. We don't have those kind of temperatures on Earth. But we're going to fix that, and the CAM people are going to fix that too. Okay, so let me give you just our take-home message. I tried to keep it short on purpose. So I think it's possible to reach these relatively high solar insolations, as you've seen, with these slow rotators, and in some cases even some of the faster ones, irrespective of the cloud parameterizations. That's the key thing. You slow down a world in these models, and you can get more or less the same results, regardless of what you do to get everything tuned at the right temperature for an Earth rotation period. I think that's an important result. I said how that's done, how these worlds maintain stability is because of a large-scale cloud buildup on the side of the star. That increases the albedo and keeps those temperatures kind of moderate. We think that the radiative relaxation timescale in these slow rotators is less than the day-night regime for those particular rotation rates. And I would say that a fully coupled ocean is not that different from our Clue flux ocean for slow and high solar insulations. And I think I had, here they are. So over here you can see some data points. I didn't have time to do all the runs. I ran 500 years just to get some kind of result. They were getting to equilibrium they weren't there, but they were close. And here you can see a data point for 10% solar increase, this red square. It's not too much below. It's a little bit cooler, which is what we kind of expect because the ocean is dealing with that increased solar insolation, the dynamic ocean. It's absorbing some of that, and it hasn't stabilized yet, so this point will probably go up a little bit. Here you see for the 64 case, it's right on it for 20%. Here 30%. At the 128-day case, it's just a little bit below. Again, I think these are because the ocean hasn't quite come into equilibrium and the 256. So I've done a few test cases with the dynamic oceans with what time I had before AGU, just to give a feel for it. Okay, and since I have a little time, I thought I'd give you a little homework. Okay, so I want you to first assume that Earth's length of day increases by 0.0017 seconds per 100 years. That's the current estimate of Earth's rotation rate slowdown. Assume the sun's output increases by about 10% per billion years, in a billion years. Let's just go to a billion years. That's what models seem to say about how our sun's going to increase in brightness. Do you think, based on what I have told you, that the Earth will still have habitable surface conditions in a billion years when you've increased its solar luminosity by 10%? This is very important, because what I didn't show you in one of those earlier plots from Koparapu and people, they're not the only ones to show this. A lot of these models are saying the Earth is on the very edge of the habitable zone, and that if things warm up too much more, we'll be in trouble. And irrespective of anthropogenic gas increases and all this sort of stuff, our sun is going to get warmer. I'm not sure we'll be here in a billion years, but if we are, the question is, will we have habitable surface conditions? And that's your homework until I see you next time. Thanks a lot for your attention.
So if you've got questions for Michael, put up your hands and I'll get around to you. And I'll ask the first one, Michael. So the way that you handle clouds at the moment, you're able to give us an idea of what percentage cloud coverage or maps of clouds?
Yep.
And
I can tell you the cloud fraction of the planet.
Right.
Yep.
And where are those clouds spending most of their time?
Yeah, if they're high or low,
Right.
I can tell you all that.
Right. So that's how do you get at that? Is that generated by the GCM dynamically?
Yes. I should say,
as for a terrestrial.
Yeah. One of the great,
atmosphere.
I should say, one of the few great strengths of our GCM is that we have an incredible diagnostics package that has been written from scratch over the last 30 years. So we can get a tremendous amount of information about what the model is telling us. I can tell you about low-level clouds, high-level clouds, how the pressure is changing in a grid cell. I can tell you a tremendous amount of things. In fact, there's so much diagnostic output that even people that have worked on the model for 20 years don't know all of the diagnostic outputs possible because our developers can just add them on the fly. So we've asked for a few additional ourselves. Like, for example, when we slowed down the planet, I wanted to make sure I knew what the cosine of the zenith angle was for the sun hitting our planet to make sure that it was changing at the rate that it should according to the model changes. I was able to add that diagnostic myself, so I could do plots of the cosine of the zenith angle, which I showed. I just showed a snapshot of it. Of this, here's what the cosine of the zenith angle looks for this particular case. So that you can add any diagnostic you want, in essence.
So there's no problem with having no dust aerosols, but clouds are coming anyway. Like, there's what are clouds condensing on?
Well, there's of course sea salt and actually, come on, honestly, we don't know exactly what all clouds condensate on.
Right.
To be honest, so
I'm just wondering.
we have some schemes in to create clouds based on observational data on Earth. And that's how most of the Earth models do things. I mean, they have mechanisms for doing that, but we're not even sure what all the cloud condensation nuclei are. There's people who say it's bacteria, right? Or other things. Right. So, good question. He's coming around.
I have a question on the opposite side from what you talked about. So Earth has definitely spun faster in the first billion years of its existence, twice faster maybe. And do faint early sun simulations take that into account? Does it matter?
Absolutely, it matters. It's one of the problems. I mean, we have problems with faint young sun for Earth. We know that we believe that Earth had habitable conditions early on in its history. And there's a lot of effort going in to figure that out. Not a lot of people, I think, have looked at the rotation rate. And in fact, until just a month ago, we couldn't do faster rotation rates. We can do that now. So we can start to look at that. But there's a belief that the greenhouse gases were different. There's a belief there was a lot of H2, maybe more CO2 in the atmosphere. Again, we don't have good numbers on what those are, but it's an active area of research and it's an unknown solution. Absolutely. Thanks for the question.
Right now, when you look at weather maps of the United States, the weather kind of moves from the west coast to the east coast in a matter of some number of days. So I was wondering if the rotation period of the Earth was slowed down, would that same effect still occur, and why wouldn't that push warm stuff from the sun side to the back of the Earth to the cold side?
Oh, the rotation rate definitely will have an influence on that. There's no question about that. Absolutely. Absolutely. Yeah,
But
you're right.
I mean,
But as you slow the planet down a lot, then it's just the radiation to get around. It's the time for the radiative relaxation for that to move just through dynamics. That's all. So the rotation doesn't help you when you're tidally locked, for example.
well, what I'm thinking is, wouldn't the warm air on the sun side be moving around to the back side?
It will eventually. Absolutely. Absolutely.
But if you're talking about
But in a different way. Remember, as I said, you just slow the planet down, you've increased the Hadley cell size also. So that has another effect also. So it will not be the same. The movement of the air will be a little different as you slow it down because you also have to deal with a different Hadley cell effect. That's going to play into the game too. These are things that have not been explored in detail yet. But it's coming. I mean, again, there aren't many models that have done this kind of work so far, but within a few years we'll be able to answer questions like that, I hope, quantitatively.
So I have a question, not so much about the output from this model, but rather how the model got produced over, 30 years?
Yeah, yeah.
So 30 years ago, things were very different for people doing programming.
Yep.
And I'm kind of curious how you've had to evolve to take advantage of multi-core and other changes like that.
That would take a long time to answer. I'm sorry.
Well, just a few highlights maybe.
A few highlights. Well, I would say, okay, first of all, I would say I've only been at the Institute about 6 years. So I wasn't there for the transition to multi-core stuff. But it has been around for a while. The original, the oldest version of the model that we actually have still running is an 8x10 grid model. And that you can easily run on a 4-core machine. We've had 4-core machines for a long time. So the more recent development has been pushed by people at Goddard Space Flight Center who are interested in, of course, people using their supercomputers efficiently. And so they put a lot of effort in parallelizing our model and making it better at those things. So we have relied a lot on them in the last 5-10 years, in essence. But yeah, it's a complex, long-term problem. I mean, this model all was started out by Jim Hansen and his group, 30 plus years ago. And of course, Jim originally was a Venus person. That's what got him interested in increasing greenhouse gas concentrations on Earth when he saw what Venus is like, in essence. So, yes, Jeff.
Kind of a related question in a way. Isn't there kind of a gloomy picture coming out of out of some of the? Is it fair to take a fairly gloomy picture out of this in a way? You have this behemoth program that's 30 years old, and the people who started it are probably gone. And
no, the people who started it are all there.
Well,
the original radiation person,
okay.
He's on the 7th floor of my building.
Okay.
6th floor, excuse me.
But
How old is he? Yeah.
Right.
Well, it's a group. Okay, I should say. Also, these are groups. These are not single people. I said in the beginning, I go talk to the PBL person. That's not really the way it happens. I go talk to the PBL group. So there is overlap between people. So even though Andy Laces, who's our radiation person, he may retire in the next 5 years, if ever. Some people, they never retire. But his group is there. They're in charge of it.
Anyway, you started by trying to kind of duplicate somebody else's results, and you couldn't even get information about so-called tuning that they did, whatever that.
Well, I should say, I confess, I did not write them. I just read their paper.
Well, okay.
And I from that paper, I tried to figure out what they did. I couldn't figure out how they got those numbers. In fact, I'm new at this, okay? I didn't even notice that point when I first looked at their plot, right?
Okay.
I just want to point this out again. I didn't notice how warm their world was. I just ran my model, I mean, I took my Earth model, I changed these parameterizations, I changed the Earth albedo and all this kind of stuff, and I ran it, and I got a very different result. Yeah. And I thought, I got better results. I can reach much higher solar insolations than they can. So they must be doing something wrong. And then my collaborator, Tony Del Genio, said, oh yeah, but look what their starting point is. It's no wonder.
Right. Well, and the other side of that is things are sensitive to these tuning parameters. You have a number of tuning parameters that you can't even give sensible names to
No,
because they're so
yeah,
obscure.
you're absolutely right. It's
So
absolutely right.
is this
I could
field
give
just-
sensible names to them, but I didn't. I
Well,
apologize.
okay.
I wrote this talk like 5 days ago because all the results just came in quite
Anyway,
literally.
should we overall be pessimistic, like I've been saying, or optimistic about how good the status is right now of understanding things?
I think that the field is at a young age, and I think pessimism is warranted. But I think already we see things from these 3D models that you could not see in 1D models, okay? So I think right now we're just at the stage where I think we're getting more interesting results and we have to explain more things than the 1D models had to explain. And I think that's where we're at. I mean, that's my feeling. I mean, I'm not a complete expert in this field, but that's my feeling. And I think that's going to improve. And it's going to take more effort and more models and more comparisons for the future to improve that.
Okay, last question.
Yeah, did you include the 4 jet streams the Earth has, and what effect did they have?
Well, I didn't look at those diagnostics, to be honest. I don't know what kind of effect they had. I mean, the model runs with all the physics that it has normally for Earth, and it has that stuff in there, but I can't tell you how that changed. I mean, I could probably plot it with the diagnostics. I'd have to figure out which diagnostic gives me that information. Like I showed you the diagnostic that gives me what the Hadley cell increase size is, so I could find out, but I don't know off the top of my head. But it's a really good question.
All right, if you have any more questions of Michael, I encourage you to come up and chat to him after he's finished here. And Michael, we have a special SETI.org/talks
Okay,
mug
wow.
for you. There's a couple of robots there that are extending the reach of the habitable zone, I'm sure, by not needing the temperatures to
I
be
think that
quite
their
as-
reach must be much farther in.
Yes.
What do you think?
Oh, definitely as
Are
well.
they made out of titanium? How far in can they go?
They look pretty shiny, don't
They look pretty
So-
shiny, yeah.
Please
Their
join me in thanking-
albedo is very high.
Right, yeah. Please join me in thanking Michael for his great stuff.
Thanks a lot.
And we'll
Here.
see you next year too. Or I won't actually